we can figure out the the electronic configuration for bromine. And we'll use the off-bow principle. That is, we're going to fill up the lower energy orbitals first, moving on to higher energy orbitals until we've run out of electrons. So I guess the first thing we should look at is the periodic table, find bromine. How many electrons does neutral bromine have? How many protons does bromine have? It has 35 protons. Each proton has a positive charge. So if it's neutral, there have to be 35 electrons to balance it out. So we have 35 electrons in bromine. Okay. We are going to fill the orbitals until we've filled them with 35 electrons. Each s set is just one orbital. Each orbital can have a spin up and a spin down electron. So that means that each of those s orbitals can have a max of 2 electrons. Each p set is 3 orbitals. So each p set can have a max of 6 electrons. And then each d set has 5 orbitals for a maximum of 10 electrons. Each f set has 7 suborbitals for a maximum of how many? 2 times 7, 14. Each orbital can have 2 electrons each. So that means that if you have a set of 7, they could have 14 max. It could be unfilled, but there's at least space for there being 14. Okay, so we have 35 electrons to fill. How many can fit in this 1s? I'm just following these diagonal arrows that keep me honest about filling the lower energy ones first. The 1s orbital could have 2. Okay. Then I'm going to fill in the 2s orbital next. What's the maximum amount it could have? 2. Okay. I probably should keep a tally somewhere. Yeah. Let me do that. So I'm just going to sum up all the electrons we end up doing. Great. Okay, so our running total is 4 so far. Whoops, let's not do that. Minus. Okay, so we'll have a running total of 4. So it'll keep going with us. So we filled up the 1s and the 2s, the arrows, we follow them and go to the next. It's this 2p. How many electrons max can you fill in the 2p? 3 orbitals, 2 electrons per orbital, so 6. Yeah, right? Okay, so I'm going to put 6 in there. We've accounted for 10 electrons. We have to keep going. We're going to 35. Next, we're going to fill the 3s orbital. How many electrons max can we put in 3s? And there's only 1 orbital, and there's 2 per orbital. Since an s orbital only has 1 orbital, there's going to be max of 2 electrons. Max of 6 again for p. So I'm just putting them in there. So far, we've accounted for 18 electrons. We have a long way to go. Okay, after 3s, 3p, next is 4s, right? I'm just following the diagonals. So 4s, because we haven't gotten there yet via the diagonals. So I follow the diagonal lines. They tell me which ones are lower in energy. So I do the 1s first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d. Yes, the ordering's kind of weird. That's why we have the mnemonic, so that I can keep track. Okay, so far we have 20 electrons accounted for. We need to get up to 35. So we went through 4s. If we follow the diagonals again, the next thing to fill up is 3d, right? So 3d. How many electrons fit in a d set? 5 orbitals, 2 electrons per orbital, 10. Okay, so now we have 30 electrons, and after the 3d, we fill in the 4p, right? 4p, we need to fill in 5 more electrons to get to 35. P can add up to 6, so we're done. If I was asked to report the electronic configuration. I would probably end up reporting it like this. So it'd be like 1s with superscript 2, 2s2, 2p6, 3s2, 3p6. All these are superscripts. All these are subscripts. I think the more proper way to do this is to do them in order of principal quantum number. So you'd be like 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, because it's 3's before 4's, and then 4s2, 4p5. So these diagonal lines tell you what the order is that you're going to be filling them up. But then when you're reporting them back, to be the most proper, I think what you do is you go by principal quantum number first. So that's how you would organize them. So if I wanted to be proper, I would actually invert this. I'd have 3D where 4s is. It would be 3d10 and then 4s2. So why don't I bother to do that? Not a bad idea. So 10, 3D, 4s2. Okay. So at this point, we can start asking questions about whether or not this makes sense, whether or not this is consistent with all the stuff you've done in class. And believe it or not, you have a lot of resources at hand to work. So looking at the periodic table again, here's bromine. What row is it in? It's in 1, 2, 3, 4, right? And what block is it in? It's in this block. It's in what's called like the P block, this thing. So if I look at the electronic configuration, and I make this, whoops, I make this small enough so I can actually look at them both at the same time. Okay, so almost. All right, better. So 1s2, that fills up this row, and then the second row gets filled up with 2s2p, right? So these 4 spaces correspond to electronic configurations that would have gotten filled up by one more electron incrementally in the 2s and 2p orbitals. Then this third row gets filled up by the 3s and 3p. 4s fills up potassium and calcium, and then this D block gets filled up by the 3d, and then you end up filling in 5 p electrons here. So the net result here is that you end up having, in the 4 principal quantum number set of orbitals, 7 electrons. And that's what we use for bromine's valence electrons too. So that makes a lot of sense, right? This is a nice way to check. You have, in the 4 orbitals, you have 7 electrons. Here you have valence electrons that are 7. It's in this column that's right before having a completed octet, so it's 7. So that's a great way to check. Another way to check, just to make sure, is that you end up having 35 electrons total. We do have 35 electrons total, so that's a good way to check as well. And that's how you do it. Let's do